we have a slit. That this you can see, these are two pieces of a razor blade, and the sharp edges are facing each other, so that there is a small opening in between. All right, there is a small opening in between. You just take a razor blade, break in two parts, or two longer on the parallel to the longer side, and the two sharp edges, they should come in the middle, and then you can prepare this kind of a slit, an opening. And if I pass light through this opening, what my school textbook says that only in front of this opening I will have light, and then I will have shadow, right? The light will go only through this opening between the two edges. So I will have some light there, and then on the two sides it should be all dark. So then I have another kind of opening, that also let me show. On this plate, this is I believe it is a photographic plate or so. In this there are some black portions, and then there are some clean transparent type of portions of different widths, and in the bottom, in fact, there are closely spaced two openings. The top part, there is only a single opening of different widths, they are separated from each other, one will be used at a time, but on that lower part there will be two openings very close to each other. Just try to have a look. That upper part you can see, the white ones are the slits or the transparent part through which light should pass. The black ones are opaque. Believe me what it is, what I am telling. The lower also we have slits. Upper ones, they are separated, widely separated from each other several millimeters. One will be used at a time. But the lower one are in pairs, two slits, then few millimeters, then again two slits, then and so on. So this is how it is constructed. Kinds of patterns which will not go along what we have been told, that light goes on straight lines, and if there is some transparent material it goes through, and if there is some opaque material then it is just blocked. Let us take that blade. Now it is not an obstacle, it is an opening in otherwise opaque area. So if I put my light here, see what is happening. Can you see those dark regions between the bright dashes? That is the thing I want to show you. Yeah, the center is very bright, but after center you have dark, then you have bright, then again you have dark, then you have again bright, and so on. Now let me take up the double slit thing. Single slit I have already shown you with the blades. Let me try with this double slit. Yeah. Can you see it here? Okay. See it this one. And notice that center is not that bright. There are two slits close to each other, and then the laser is falling on both the slits, and then there is opaque area, and have this distinction. See, the center is not that bright, correct, and they are all equispaced. But if I do it for a single slit, this was the case. The center is much brighter and wider, and then you have small these things. So that difference in pattern you should note. Yeah, now we can put on the light. Okay, so let us understand where our school textbooks taught us wrong things. And the light is not going in straight lines, it is not casting shadows, it is not going through slits the way it should have gone. So now we start with the character of light in much more detail. We say that light is not like particles which go in straight line if there is no force on it, Newton's law, but it's a kind of a wave. And the wave is in terms of electric field and magnetic field, right? And how much is the electric field? Together with this question, I must specify two things: where and when. Okay, if the light is coming from this source to me, then in the entire room there is light. So if I ask how much is the electric field or how much is the magnetic field, where? Here or here or here or here or here. So I have to specify the position where I am asking these fields. Then when? You specify the position, but then as a function of time it keeps changing. The electric field keeps changing and the frequency of change is very high. How much? Normal visible light, how many times per second this electric field will oscillate? Any idea? The electric field will fluctuate from some plus value to some minus value.
Speed of light divided by wavelength of the light.
Tell me the number. 50 times, 100 times, 1000 times, billion times, trillion times. It is close to 10 to the power 14. Somewhere between 10 to the power 14 and 10 to the power 15. Depends on which light you are looking at, green light or red light or violet. So it will be around 10 to the power 14, 15 times per second. Electric field reaches its maximum, then comes down, becomes 0, then it inverts the direction, then again it goes to maximum in that direction, then again its magnitude starts decreasing, it becomes 0. So the cycle goes on. In 1 second it does 10 to the power 14 or 10 to the power 15 of that of oscillations. So if I ask how much is the electric field at this point, immediate question is give me the time, and very precisely, ask for a very precisely. Don't ask at 2 seconds or 3 seconds. You have to give me precision of 10 to the power minus 15 seconds. Otherwise, it will so many times it will change its value. So we write an equation, and if the light is going in x direction, if light is going in x direction, then the electric field is written as some magnitude E naught, let us write, sine cosine k x minus omega t. So if you tell me the position x, this is the point where I need electric field. If you tell me the time t, this is the time at which I need electric field, I will put in this equation all those things and I will tell that okay, at this instant, at this position, this is the electric field for light going along x axis. But then electric field is a vector quantity, so it must have some direction. And it turns out that if light is going in x direction and if it is in free space, air, or a good dielectric transparent medium or vacuum, then the direction of electric field and also magnetic field are perpendicular to the direction of motion. So we can take this as in say y direction. I cannot take x direction, I can take y direction, I can take z direction. Any other direction I can take? Given that electric field is perpendicular to the direction of propagation and the direction of propagation is along x axis, I can write the electric field direction as y direction, which I have done, or z direction, which I can do by putting j cap in place of k cap in place of j cap. Any other direction I can write? What? Yes, j cap plus k cap, that is also perpendicular to x direction. any direction in yz plane is perpendicular to x direction. Y axis is perpendicular to x axis, z axis is perpendicular to x axis, but any line in yz plane is also perpendicular to x axis. All the lines in yz, that's why we say that x axis is perpendicular to the yz plane. Any line is okay, but let's take this one. So this is how it goes, and you have to of course take some proper t equal to 0, x equal to 0. That choice is ours. Any position I can say this is my x equal to 0, any instant I can say this is my t equal to 0, and then the position and time which you are specifying will be measured from here and at this, from this instant, and then we can say what is this. Okay. Okay, now what is this k business? What is this k? This k is related to wavelength. Remember, this is oscillatory sine function. So at a given time, at different places, you have different electric fields, somewhere positive, somewhere negative, depending on how, if you change x, this angle is changing, this thing is changing, and therefore the sign is changing. And if you keep on increasing x continuously, so it will keep on changing, and therefore this electric field will be oscillating from plus E naught to minus E naught as you go along the x axis at the same instant, right. So the distance after which it is repeated, that is lambda, and this k is related to lambda according to that. And what is omega? Omega is 2 pi by capital T. Capital T is time period. Means, now focus at one point, be there, electric field at a particular x. As time passes, the electric field there will keep on changing, and there also sign is there. So if this t keeps on changing continuously, regularly, and it has to change, then this angle will keep on changing continuously, t is increasing. And as this changes continuously, once again this electric field will change from plus E to minus E in a oscillatory fashion. So this capital T is time period, after what time it repeats its value, and also whether it is decreasing or it is increasing. So one full time period of oscillation, that is this capital T, and this omega is related to this time period. Omega is 2 pi divided by capital T. Yeah, significance of k, that is what I told, it is 2 pi by lambda, it is related to the wavelength. What is wavelength? The wavelength is the distance after which the electric field is repeating in x direction at a given time t. So that is how that k comes into picture, right. So lambda has got, wavelength has got a significance, and thus k is just inversely proportional to lambda, definition 2 pi by lambda. Okay. Third thing is speed. This omega by k, this turns out to be the speed of light. Okay. Then the intensity of light is half epsilon naught E naught square c. Epsilon naught, you know, 4 pi epsilon naught. So that same number epsilon naught. E naught is this amplitude, this E naught here. Intensity means what? If I put an area, light is falling on it perpendicularly, how much energy is falling per unit area per unit time? Okay. So take some area and let light fall for some time delta t. How much energy has fallen? Divide by delta A, divide by delta t. That is called intensity, energy falling per unit area per unit time, that is intensity. So it is proportional to the amplitude of electric field square. But there is one thing, that if it is not a free space, there is some obstacle or there is some opening, part of the light is obstructed and part of the light is allowed to move, then of course this equation will not hold in its form. How to get what is transmitted on the other side? This is the problem that we have started with. I had an opening and I send a light, and then on the other side I find there is a peculiar pattern. It's a peculiar pattern. There are some specific directions are chosen by light and some are not. So I should know how to deal with this. Okay? Or if I put an obstacle, so I am allowing light from the two sides of the obstacle and then collecting it on the other side, and I again find some pattern. And if I give two openings, then it's a different kind of pattern. So I should know how to construct that later wave if there are obstacles and openings. If part of the light is allowed and part of the light is not allowed, then what happens? This equation is for the free space, right? No obstacle, no slit, no opaque things, etc. It's for the free space. Now, I just give you the recipe, and the recipe is that if look at the allowed portions of light which is allowed. Suppose this portion is allowed. So I am talking now of single slit. So originally there was a wave, and this wave was given by this kind of equation, but now you have only this much of opening. This is all opaque. So only this part is there. Part of it is obstructed. Then it says that treat each small part of this opening, whatever is opened. If it is an obstacle, on both sides you have to do the same thing. Whatever is opened, treat that as small part, small part, small part, and from each part light is going in all directions. From each part light is going in all directions. Okay. Initially light is going only in x direction, but then part of it is obstructed and part of it is opened. Now how to find what is happening on the other side of this element that I have put? For that, the recipe is, from the open part which is allowed to move further, you treat those open parts bit by bit, and from every bit you think that light is going in all directions. Okay. Then if you are asking me how much light will reach here, so from this portion light is, the one which is going in this direction is not reaching here, the one going in this direction not reaching here. So from every point you have to connect this particular point. Other things you forget, you only look at these things. There is an electric field here because of each of these individual components. Those electric fields are to be added, and then you have to get the resultant electric field, and then you have to see what is that amplitude of the resultant electric field, and then you have to see what is the intensity, right? A serious recipe, not very simple, but it works. That whatever is allowed to move further, from just looking at that element that I have put, one slit or two slits or an obstacle, a wire, whatever is allowed, what is open, from that open part you divide it small parts. From each part it is going in all directions, no more in x direction, and there is a point somewhere you are collecting the light. Okay. From all these bits you connect that. So the electric field is reaching from here, from here, from here, from here. Add all those electric field there vectorially at a particular instant. Don't add electric field at time t1 to the electric field at time t2. That is not physically meaningful. Okay. So at a given instant of time, whatever is reaching there from all these openings, that you have to add vectorially. That will be the final electric field at that point. Look at its amplitude and you get the intensity of there. When we do that, then we can explain all these patterns that you have seen. Yes.
The light would sort of bend, and that is why, because it's a curved wave, it would cover more area than expected. So this is a bit different from what you're saying. So could you just
it's not different. Those are the results that you are telling me, and I am telling you the method to get those results. Okay. You are telling me that, okay, if the slit size is comparable to wavelength, then this will happen, that will happen. right? But this is the way you get to know the quantitatively what is the intensity there and what is the intensity pattern there.
So it's the same thing.
It's not the same thing. I am giving you see, you are giving me the destination, and I am giving you the way to reach that destination. Destination I had always shown you, already shown you. This is the kind of patterns that is there. Then I should know how these things are being formed. Why there are certain places where there is no electric field. Between those two dashes you have dark. No green light is reaching there. Why it is not reaching there? On this side it is reaching, on that side it is reaching, and in between it is not reaching.
Is it because the sum of the amplitude of the
We will do that. That is what we are doing. That is what I am telling you.
Sir, so can you consider like any wave, sort of like you can consider obstacles on both ends and there's like an infinitely open part in the middle. What I'm saying is this only applicable when you can see the two obstacles?
No, this wave, any way you obstruct it. If it is a free space, fine. It's going in x direction, you know how the electric field will change with x and with time. And anywhere you are putting a screen, what is the electric field. But if part of the wave is obstructed, part of the wave is transmitted in whatever way, right, a circular opening or two openings, annular ring, edge, one whole plane is opaque and this whole side is open, whatever way, once you obstruct, this recipe will work. Okay. So that means if this is the line which gives me electric field at a given point beyond that optical element, then if I have two slits, for example, then I should get that pattern from here, right? If I have a single slit, I should get that pattern from here, right? And suppose I have a slit which is very, very narrow. So for that, the light will go uniformly in all directions. Okay, uniformly in all directions, and if you are collecting it at a very large distance, suppose here you are collecting, so here, your intensity will be uniform, no dark patches in between, right? Your slit, your opening is so narrow that it's one element, dx. What do we say? We say if you have an opening of say 0.1 millimeter, 1/10 of a millimeter, which is very large as compared to the wavelength. So that has to be divided in micron, micrometer, and then from each part you take what is the contribution in all directions. This is only one point. It itself is very small. Say 1 micron. Itself is very small. So no need of doing all that algebra. Your intensity will be uniform in all directions. It's just like a point source emitting light in all directions. Of course, in one half only, not on the other half. It is a slit, of course, it is slit. And I am sending light from one side, a parallel beam from one side in x direction. Other side it is going everywhere. Okay? Yes. No. Monochromatic ray means the light does not have a mixture of different wavelengths. Monochromatic means one single wavelength. The light which you are receiving from these ordinary sources, they are having components starting from 400 nanometer wavelength to 700 nanometer wavelength. You also have components beyond these limits, but they are not used for seeing things, but you do have components there also. So many wavelengths are mixed up. That is non-monochromatic. Monochromatic means just one wavelength.
So why is it that after you obstruct a ray of light, it starts moving in different directions? What's the reason for it?
Okay. Okay. Now, see, it's a very complex question, right? And it's very difficult for me to answer that also. But let's think there is no obstacle. It's going in free space. What is light? You have electric field and magnetic field. So I have electric field here fluctuating. Why should there be an electric field somewhat distance ahead? Why? What is traveling? The electric field is oscillating in y direction, magnetic field is oscillating in z direction. What is there in x direction? No particles. There are no particles. There are no particles. Newton told that there are particles. But then Young in 1801 did an experiment which I am showing you, that double slit thing, and then people knew that okay, they do not have particles. That another very interesting story. Newton in late 17th century put this, that light is collection of particles, they are going in a particular direction. But then when after 150 years or 130 years Young came, and Young did this experiment, and then people came to know that no, nothing is going in that way, it's some kind of vibrations in some ether or something. Wait, the story is not yet complete. So since then, the year 1801 onwards, right, the students were getting full marks for writing light is not particles, light is not collection of particles, light is a wave. What kind of wave? People did not know. What kind of wave? People did not know. But it has to be wave. Just like sound wave, it has to be some kind of wave. So that particles have gone. So waves. Now the questions were which wave, which wave, which wave? And then Maxwell comes in late 19th century, develops electricity magnetism theory, electrodynamics, and from there he tells that look, here it is, this is light, it is electric field and magnetic field, it comes from my equations. Okay. So that late 19th century people started saying okay, good, from Young's experiment we were knowing that these are waves, and now from Maxwell's theory we know that okay, these are waves in terms of electric field and magnetic field. Right. So I am using that picture of that area, late 19th century. So it was that. Then what happened? Again students were getting full marks for writing that these are waves and these are electromagnetic waves, and electric field and magnetic field are perpendicular to the direction of propagation and blah 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 blah. Then Leonard did some experiment in 1897. These experimentalists, they don't have any other job. They will keep doing something without any plan most of the time. But when they do, something will come up and then will shake the whole world. So when he does this experiment, so-called photoelectric effect, shining light on certain metals and electrons coming out, and those results, this electromagnetic theory failed. So the great puzzle, whether it is particle, whether it is wave, if I put that metal and shine light on that, it looks like it's not wave. But the same source of light, same lamp, same physical piece of lamp, same lamp giving the same light. On one side you put this metallic sheet from where the electrons are coming, and from the other side you put that two slits, so that you see that intensity variation there, pattern is the same source of light which is giving light here and light there. And if you think that there is something wrong between this direction or this direction, you can rotate the whole apparatus by 180 degrees. So this side is Young's double slit and that side is metal foil, even then you see the same thing. The double slit experiment cannot be understood in terms of particle picture, and this photoelectric effect cannot be understood in terms of the wave picture, and they are both happening side by side. Then comes Einstein. 1905, and then he says that okay, झगड़ा मत करो, it's both waves and particles. ऐसे ही करते हैं ना, when two people are quarreling और हम बीच में जाते हैं बीच बचाव करने के लिए, कोई नहीं, तुम्हारा भी है दोनों के. So Einstein does that job. Okay, it waves and particles, it depends It depends what condition you are putting the light in. Okay. Every person has certain bad character inside and certain good character inside. The person is not good or bad. It is the which you are putting that person. If you are putting the person in a very aggressive, people are abusing this person and this and that, he can also fire back and can show aggression and this and that. But if the same person is there in some satsang, very docile. So it's not fair to ask whether the person is good or bad. It depends on the condition the person is put in. So don't ask whether light is wave or particle. It has both of them inside it. But depending on what condition you are talking, what condition you are putting that light in, either the wave property will be there or will show up, or the particle property will show up. Now, when I am talking of this double slit, single slit, passing, etc., is the wave property that shows up. Yeah.
So, in the double slit experiment, well, light does show the wave property and we get an interference particle. But if suppose it is a measuring, it is an observation device, then in fact, you will notice a different observation. Light continued to act like a particle under just because it's being observed. So it changed its nature just by the act of observing.
No, that's right. That's what I am telling. If you are putting this light in a different condition, different experimental conditions, it will behave differently. If there is no person to observe, I can put off my shirt and then I can very relaxed, in a relaxed fashion, I can live in my room. But if there someone is observing me, I will not do that. I will put all my jackets and everything. So once the observation measurements are there, light also is very sensitive to that. It will behave accordingly. If there is no one to observe, it will behave in a different fashion.
So has there been like a...
So don't ask what is the objective reality of light. The message is, don't ask objectively what is the character of light. It all depends on the environment with which it is interacting. Okay. So a single slit with a very narrow opening will give you equal intensity on the screen. No dark patches and these things. Now next simple thing to analyze it, and we will do it somewhat quantitatively, and that is, you have two very narrow slits separated by a distance. So you have one slit. Once again, it's very narrow. So I am only showing you a magnified version. And then I am looking at the screen here. So this is the central point. So from this slit, light is going in all directions with uniform intensity distribution. From this also, light is going in all directions with uniform intensity distribution. Now I take a point on the screen and ask, what is the intensity here? So what is the electric field here? So I will join this point to these two slits and then ask, what is the electric field reaching at this point P from the first slit? What is the electric field reaching from this at this point from the other slit? We'll add it vectorially and see what is the resultant electric field, right? That is the method I have to use. So from here, this particular light wave will be picked up, and from here this particular light wave will be picked up, and these two electric fields will be there. Why it is very difficult to draw straight lines on this board? Had it been a green board and a chalk, calcium carbonate chalk in my hand, I could have drawn much better straight lines. Friction is less here, okay. Friction is very small here, and I am not allowed to go the way I want to go. But if it is chalk, I can draw much better. So if you understand those rules, those laws, those equations of friction or whatever things you learn, and you look at what you are doing in 24 hours, there are hundreds of places where you can apply those equations, and you see that yes, nature goes according to the laws I learned in my class, and it will be very enjoyable once you start doing it. How I can holding this, and how I can sitting, how can I standing, and what else. So there are hundreds of things you can apply those things. Once you start doing that, you will really enjoy the physics. Okay. So light is coming here, light is coming here, and here it was all unobstructed and this and that. So whatever was phase here at time t, the same phase is here at time t. What does it mean? It means that if this light is written as, say, E equal to some E and some j cap and some sine kx minus omega t, right, and this is the y direction or z direction, nothing changes if you go from here to here to here to here, in this equation at least. It changes only with x, correct. So this slit to this S1 to S2, I am moving only in y direction, not in x direction. So at a given time and a given x, this angle is same, and therefore this E is same. So here and here electric field is same at a given instant. Now from here it comes up to this point, from here it comes up to this time. X1 is smaller, X2 is larger. What is here at the same time will reach point P at two different times. One has to travel a length x1, other has to travel a length x2. They are reaching at two different times. Those electric fields I cannot add. I can add the electric fields at P at the same time, coming from slit S1, coming from slit S2. Right? So if I want the electric field here at a certain time t, I want electric field at P at a certain time t from S. So let me write it E1 at P at time t from S1. This must have originated from S1 at a time t minus x1 by c. Because it takes time x1 by c to reach that point P, starting from S1 to reach that point P. So this is same as E at S1 at time t minus x1 by c. Whatever is here at this time, whatever he is at S1 at this time, the same thing will reach point P. It will travel a distance x1 in time x1 by c, and it will reach there. So the electric field at P at time t is same as the electric field at S1 at time t minus x1 by c. And similarly, E2 Pt from S2, the electric field reaching P, starting from S2 reaching P at time t, I must take the electric field at the same instant I want to add. Okay, at P I want to see the resultant electric field. So at time t, what is the electric field coming from S1? At time t, what is the electric field coming from S2? So the electric field at P at time t originated from S2 at a time t minus x2 by c. So this is equal to the electric field at S2 at time t minus x2 by c. Now these two are different times. So if I write this, it is remember here our equation is this. So this is equal to E j cap sine kx, x is same here and here, and minus omega t, so minus omega t minus x1 by c. This x1 is x1 for this x is for these things, x here. And similarly, the second one is E j cap sine kx minus omega t minus x2 by c. So, the electric field E at point P at time t is equal to, now I am taking the resultant electric field, is equal to E j cap and then sine kx minus omega t and plus omega x1 by c. Yeah, and plus sine and then k x minus omega t and plus omega x2 by c. I have added vectorially, both of these were in j cap direction, so I can add the magnitude. The whole thing will be in j cap direction. This x I am writing for the slits, this position, this time, right? This is the resultant electric field. Now it's a matter of trigonometry, which I am not going to do. And if you do this trigonometry, what you get is the following. Okay. Now if you do the trigonometry here, you will get the following. Define a quantity delta, which is the difference between these two angles, right? And the difference is omega by c x2 minus x1. Right? You just look at this angle and this angle. The difference is just omega by c common x2 and minus x1. That's the difference. We call it phase difference between the two waves reaching P. This quantity is called phase difference. This angle itself is called phase. So, phase difference between the two waves reaching P at time t, or and see, this is independent of time. The time does not come here. This is at time t, but then the time does not come here in this delta. So, the phase difference remains the same. So, if you define it that way, then it turns out your final, this EPT is equal to, okay, let me write some E naught. Did I write E naught earlier? No. Some E naught and then j cap, and this will be sine of kx minus omega t and some other number which will be in terms of all these quantities.
Sir, in book nowhere they mention why this phase constant is constant, why it is 0. Actually, none of the book mention this, what you are teaching right now. In fact, I also understood now. I used to say that, you know, this is a by law, by this, but why this is 0 or constant, no book explain this.
What is 0?
I mean, either phase is constant or they do reach with
phase difference remains constant.
Phase difference. They never
at a given
explain.
P, if phase difference remains
They
constant.
just define and they proceed like.
Normally what people do in books, they will say this is x1, this is x2. So, there is a path difference. There is a path difference, it has to travel greater path, and therefore, the phase is different. Yes, if it goes a distance x, there is some phase. If it goes x plus delta x, there is some. But it is not that it is going smaller path, so the phase has advanced by a smaller distance, smaller number. It has gone longer path, so the phase has advanced by a higher quantity. No. In fact, they are reaching at different times, you cannot combine. What started from here at the same time will never reach there at the same time. You cannot say that, okay, this wave has gone smaller distance, so there is a smaller phase advance, and this is a longer distance, so there is a longer phase advance, and therefore there is a difference. That phase difference, I am not interested. This is the phase at time t and t1 and phase at time t2. What do I do with that? So I have to make sure that I am adding the two electric fields at the same time. If star 1 has a temperature of 4000 degree and star 2 has a surface temperature of 5000 degree, I cannot add them and say that, okay, the resultant temperature is 9000 degrees. Nothing is at 9000 degrees. There are two different positions. Similarly, they had electric field at two different times. How can I add that? All right. So, finally, your final results are okay. It's the same thing. But the physical interpretation, how I understand it, how I reach it, is that path is different. Now, this E naught, this is the amplitude of the resultant wave. This is now the resultant. This is the after addition of those two. And this turns out in terms of this E, this E naught will be how much? E naught square will, E naught will be 2 times E and cos of this delta by 2. It is all trigonometry, I am not doing that. No physics is there. So, with this delta defined this way, this amplitude will come out to be this. And hence, if I talk of intensities, suppose I block one of the slits. I block one of the slits. Then no question of adding. It's coming only from one slit, and that is just one part of it. This is your final electric field. So amplitude is E.
Now intensity is proportional to square of the amplitude. And how much is the amplitude when one slit is open? It is E. How much is the amplitude when both the slits are open? It is E naught. And what is the relation? E naught is 2E cos delta by 2. So square both the sides, and remember that E naught square is proportional to the intensity when both the slits are open. E square is proportional to the intensity when only one slit is open, and therefore when you square this equation and write in terms of intensity, it becomes I naught equal to 4I cos square delta by 2. It does not match with what is given in the books. So let me switch. When one slit is open, let us take the intensity as I naught, and when both the slits are open, let us take it as I. So that you have I equal to 4I naught cos square delta by 2 as given in the books.
Once again the diagram, my two narrow slits, and then at a large distance I have this screen. This is S1, this is S2, this is a central point. Remember, delta is k times x2 minus x1, or 2 pi by lambda times x2 minus x1. At this central point, which is symmetrical, equidistant from S1 and S2, x1 is equal to x2, delta is 0. And if delta is 0, cos square delta by 2 is 1, and I is 4 times I naught. Here I is 4 times I naught. Block one slit, it is I naught. Allow only the upper slit. Block the upper slit, allow only the lower slit, it is I naught. Allow both the slits, it is 4 times I naught. That is constructive interference. As you look at the points which are away from the central point on the screen, the difference between S1 and S2 will start appearing. It was 0 at the central point, but now it will increase. slowly, continuously you go up, it will increase. At a certain point, this x2 minus x1 will become lambda by 2. It's continuously increasing from 0. So if you are using 400 nanometer light, at a certain point on the screen, x2 minus x1 will become 200 nanometers. At that point, this will be lambda by 2. So it will be what? It will be pi. And if delta is pi, this will be pi by 2. And cos of pi by 2 is 0. So at that point, no light will reach. That is destructive interference. You go up, delta will further increase. From pi, it will increase to some other value, so that this will no more be pi by 2. Cos delta by 2 will no more be 0. So again, intensity will start appearing. And at a certain point, delta will become 2 pi. Delta by 2 will become pi. Cos of pi is minus 1. And cos square of pi is again plus 1. So again 4 I naught. So you will have 4 I naught, then 0, then again 4 I naught, again 0, again 4. And they are all equidistant. These are all 4 I naught points. And in between you have those 0 points, 0 intensity points. And between 0 and this 4 I naught, the intensity will gradually increase. Right? It's not either 0 or 4 I naught. From 0 to 4 I naught, it will gradually increase. Then it will again go to 0. Then it will again increase. What we see, is not this kind of fluctuations in intensity. We see complete dark in some distance. It's not that at one point it is completely dark and then I see intensity. And then once intensity is there, I see almost uniform intensity for quite some time. These are because of limitations of our eye sensitivity. Very small intensities we are not able to observe. So we don't see a point as completely dark, but a range around that point as completely dark. We are not able to receive those small signals and then amplify and get that. Then there is an upper limit also. If there is certain intensity level is reached, then after that, as intensity increases, we are not able to really see that yes, there is small variation in intensity. So those limitations are there. One can record the electric field amplitude using good electronic sensors, and then one can see that yes, it goes like that. Okay? Yes. Questions?
So you can prove this mathematically, but how do we theoretically prove or explain it?
Theoretically, I told you what I have done.
It's mathematics.
Yeah, mathematics. But before math, I told you at what point I deviated. I said that now it's all trigonometry, no physics in it. But before that, it was all physics. This expression has come from the physical phenomena, that your single narrow slit is giving intensity in all directions uniformly distributed, and then you have two of them, and then the electric field here must be sum of these two electric fields there. Vectorially you have to add. All this is physics. Okay, and then now I am calculating how much is the intensity. I cannot do away with mathematics, right? If I have to do physics, I cannot do away with mathematics, but the physical phenomena I must understand first, and then I should do the proper mathematics to get the quantitative result. The physical phenomena is that the two waves which are reaching here had originated at these slits at different times, and since they had originated at different times at the same place, so their kx minus omega t were different, because they originated at different t. And if they are different, and then there will be situations when one is giving me electric field in this direction, other is giving me in this direction. There will be situations like that, and then the two electric fields will vectorially add to 0. right? And if there are situations in which both these are aligned, then it will be double of the amplitude. I am adding electric field vectorially, and intensity is proportional to the square of this. So you have a lot of physics involved. Mathematics is only just to give some assistance to reach that final thing.
I understand what you were saying about how because x2 is greater than x1, we'll take different amounts of time. But why are we calculating it as t minus x1 upon c and t minus x2 upon c?
Okay. Okay. So let me repeat. I have these two sources. Up to here everything is fine, right? At a given time, up to here, at a given time, the angle here, the angle here, angle means kx minus omega t, of which I have to take the sign. That angle here is same, because kx minus omega t does not depend on y. X is same for both the slits, and at the same time t I am talking. So at any given time, this phase or this angle is same as this angle. Okay, but I am not interested in that. What I am interested in, what is the electric field which is coming from here, and what is the electric field which is coming from here. But then I know about these things certainly. Here I know that it is going at sine kx minus omega t. So give me time, give me x, I will tell what is the electric field. At this point, give me x, x is already given. Slit is fixed. So x is already given. Give me time, time is changing. So give me time, I will put that time here and get, I can tell you what is the electric field here. So to get the electric field here, I am coming back in time when this electric field was originated at slit S1. And then I find that the electric field which exists here at time t, that same electric field existed here at time t minus x1 by c. Because light takes a finite time to reach from S1 to P. The distance of S1 to P is x1 and the speed of light is c. So it will take a time x1 by c to start from S1 and reach P. Correct, correct. So I am interested in the electric field at point P at time t. Now this same electric field was originated at S1 or started from S1 at an earlier time. How much earlier? It had traveled a distance x1 at a speed c, so x1 by c earlier. So there it was at time t minus x1 by c. Now my question is, at S1, what is the electric field at time t minus x1 by c? Now I have a formula that at S1 and S2, the electric field at position x, of course x is fixed, and at time t is sine kx minus omega t. So in place of t, I put t minus x1 by c, and I get the electric field there at that earlier time. Same thing I do for electric field reaching P at time t, but originated from S2. For that, this time is different. But it is S1, S2 is the same formula will work, kx minus omega t. Only thing I have to put proper value of time. So I put the proper value of time t minus x2 by c. Please repeat. She is asking the phase at S1 at time t minus x1 by c, is it the same as the phase at P at time t? Okay. When we say the wave is moving with a speed c, that is precisely the meaning. Whatever, if the crest is here, if the electric field is maximum here, right, and in time t, the wave has traveled a distance ct, that means this crest has reached there. So So if this is crest, that is crest. Okay.
So just for clarity, what I mean is, will this pattern continue till infinity, and is the reason why
No,
we
no,
didn't
no,
see
no.
it there
Okay.
due to
Yeah, okay. See, one thing is I am using a plane screen, and if you are using a plane screen, then the distances themselves are different, and if it is diverging, the intensity will go down as a function of distance 1 by r square, etc. So that's one reason. There is another reason which I will be just coming in maybe 3-4 minutes.
Way of explaining, where does the coherence of sources come into?
I'll come. That is what I told. In 3-4 minutes perhaps I will be talking of that. Okay, right? So I have explained that double slit pattern, and you see, since it is all same, all the maxima are at the same intensity, of course in the small region, right, and they are all equidistant. And to remember the double slit, I can repeat it. There was a small region in which you had lines all equidistant and no bright thing in the middle, right? No bright thing in the middle. That is a double slit. So that is explained by this kind of equation that we have developed, right? Now there are certain issues. I am now coming to that coherence part, and the issues are, when the light is originated from a source, that it is because, generally it is because of some group of atoms de-exciting from a higher state to a lower state, correct? So suppose there is some group of atoms in the excited state, and somehow they have gone to the ground state emitting this light, okay? But then this group of atoms can emit only a finite amount of light, a finite energy of the light, and that finite energy cannot go for maybe 1 kilometers. If you have a wave in 1 kilometer, E equal to E naught sine kx minus omega t, and intensity is that much, you can calculate energy density and so on and so forth. So if there are some, say 10 to the power 15 atoms at this state and they are de-excited, there is a finite energy. That finite energy will be in some finite distance contained. You cannot have much longer wave of that continuously, and that will last for maybe 10 to the power minus 8 seconds. You know, the lifetime is of the order of 10 to the minus 8 seconds. So it falls. Now another group of atoms can go in excited state. Of course, when you are continuously heating the gas or heating something so that light continuously comes. If your bulb is there, filament bulb is there, or some ionization is there, so you are supplying, you are making them go to excited state, and then they are coming back. But then one group of atoms which has de-excited, and then another group of atoms, they do not talk to each other. They are independent of each other. This one group is okay, all of them are in excited state, so maybe they are cross talking, and therefore there is some kind of a resultant light coming and so on and so forth. But if the entire group is changed, right, the whole army of these atoms is now changed. It is a separate management. So you will have a totally separate results. So that means you have kind of a finite wave trains. You do not have infinite waves represented by a sine kx minus omega t. That still you can work with sine kx minus omega t if you are not near the end of that wave train. In the middle portion, yes, okay, but then it will end, and another wave train will come from another group of atoms, And on one train, okay, you know that since sin kx minus omega it is applicable, and so at this point if I see the phase at time t1, I see the phase at time t2, I know it is governed by that kx minus omega t. Put t equal to t1, put t equal to t2, take the difference, that is the phase difference between the two electric fields which existed here, one at time t1, one at time t2. Okay. But if I take time t1 and my time t2 is much later, in all probabilities I am not on the same wave train. T1 is on this wave train and T2 is on some other wave train which was behind. This wave train has gone, its tail has also gone, and another wave train is now at this x. Okay. And this wave train and that wave train, they do not have any phase relationship, they are independent of each other. So omega t2 minus t1 will not be the phase difference in that case. Right? Similarly, at a particular time t, at a particular instant, you take 2 points x1, x2, and you think that okay, I put x equal to x1, phase is kx1 minus omega t, and if I put x equal to x2 at the same time t, the phase should be kx2 minus omega t, and the difference should be k into x2 minus x1. But if this x2 minus x1 is too large, much more than the length of the whole wave train, then your x1 is on one train and your x2 is on the other train. And then that k into x2 minus x1 will not be the phase difference, right? So all these things that I have told is valid only if this t2 minus t1 or x1 minus x2, so to say, is quite small. How much small? Now that depends on the nature of the source. For normal sodium vapor lamp which is used in laboratories, this length of wave train is somewhere about 1/5 of a millimeter, 1/5, 1/6 of a millimeter, or 1/4 of a millimeter. That is the kind of length of the wave train. It is very small from our standards, but then remember, your wavelength is the right parameter to compare with. Wavelength is only it is sodium light 589 nanometers, less than 600 nanometers. So 1/5 of a millimeter is quite a long distance that way. But for our doing experiments, 1/5 of a millimeter is a very small distance. But if you have lasers, that length of the wave train can be 10 meters or 20 meters or 50 meters. So it depends on the source. Right? But keep in mind, if you take your double slit, or even that double slit is here, and you had asked the question, what does it extend up to infinity? And I said that 3-4 minutes I am coming to that. Now that 3-4 minutes time is come. Now if I am a very large distance and the path difference is very large, say this is very large. First let's make this very large. Suppose this is 1 centimeter and I am using sodium vapor lamp. Okay. And I am here also, I am not close to this, I am at a large distance. So that phase difference is, the path difference is large. And therefore correspondingly, when I do that back calculation in time and I come to S1, S2, the time difference will be large, x2 minus x1 by c, omega into x2 minus x1 by c. And the time difference is large, maybe I am sitting at 2 different trains. I am looking at the same x, but wave at t1 and wave at t2. But if t1 minus t2 is large, the first wave train has gone and the next wave train is here. So I do not know what is the phase difference. It becomes random. If it becomes random, then all this calculation will not hold and you will have a uniform intensity 2I0 everywhere. You will not have that constructive interference and destructive, because at the same point P, as a function of time, the phases will change, phase difference will change. And if as a function of time phase difference is changing, it is varying between 0 and 4 I naught. Remember, the frequency there is 10 to the power 14, and this time period, lifetime is 10 to the minus 8 seconds, and so on. So if it keeps varying as a function of time between 0 and 4 I naught, what I will see is only 2 I naught. Okay? So this is called coherence. If the phase difference between the two waves is independent of time, then we say that yes, these two waves are coherent. Even if their individual phases are randomly changing, the difference remains constant, remains independent of time. We say that the waves are coherent. There is another story to this coherence, that suppose I have a source, and the source is this big. This is the source of light, and I am looking at say this point. Now light is reaching from this portion of the source, light is also reaching at this portion of the source. And maybe if I have a filament bulb, and this portion of the filament and that portion of the filament, they are not talking to each other. It's independently, it's heated, it's radiating, it is independently radiating. So what is the phase here? Something is coming from here, something is coming from here, and these do not have any phase relationship. So it's difficult now. Now it's not coherent. Okay? So if you have this kind of source, and you think that this is S1, this is S2, it's not going to work. So you have to have a narrow source first. From the narrow source, if you need wide, put a lens and make it wider, aperture you can increase. But at the source itself, where the atoms are de-exciting, you have to have a narrow source, otherwise your initial beam is incoherent. These things will come. With lasers, these problems are much less, because laser, the coherence length is, train length is much larger. For quite some time they will be in coherence and so on. Okay? So that is it. Okay, that single slit thing, I talked about a very narrow slit, so that I don't have to do that bit by bit addition and so on. But if it is slightly wider slit, so if you have this kind, and then you are looking at the intensity here, then you should take care from here, take contribution from here, 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 here. I had shown you to some extent, leaving out some trigonometry, that if you just add 2, what happens? Now you have to add many, right? You take dx, 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 dx and integrate over this. It's not countable 1 or 2 or 3 or 4. It's a continuous opening, but then opening is large enough. So you have to take some element of this slit, and from this element you see how much is the intensity here, electric field, and not intensity, electric field at this point P at time t. Same calculation, right? Same calculation. For this you ask what was the electric field here at an earlier time, and that time will depend where you are. So if this distance is x and this is dx, then that time will depend on this x, where you are. And then after writing, you integrate over x, going x equal to 0 to x equal to the width of that slit, and then do the integration, and you find the intensity here. If there were just 2, I just added sine kx minus omega t sine kx, whatever, there's just 2 where we just added trigonometry. Now it's a continuous opening, and I have to take this contribution from here, 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 here. So you know the method. You have to take a small element, write its contribution, and then integrate. When you do that integration, your result is the following. Your I is equal to, intensity is equal to sum I naught. There's only one slit, so don't compare that I naught and this I naught. Sum I naught, and then it is sine square beta by beta square. and beta is pi by lambda, and b sine theta or d sine theta. B is that width, b is the total width of this slit. And what is theta? Theta is this angle. So theta decides p. At what point you want intensity? Join that to the center, and with this x direction see what is the angle. So this theta, this p, one-to-one relation. For each p, you just join and see what is this theta. So if I want to know the electric field at p, I find theta from here, first thing. Then I find beta from here. Lambda is the wavelength of the light, b is the width of the slit, and theta I have already taken. Then I get this beta. Then this beta I will put here, sine square beta by beta square, and I'll get the intensity, electric field at this, intensity at this. And then you vary theta, go up, go down, and this and that, and this. This if you plot as a function of theta or sine theta, it turns out that your intensity will be like this. This is theta equal to 0, sine theta equal to 0. This is sine theta is equal to what? Lambda by b, 2 times lambda by b. Similarly here minus lambda by b, and so on. These are all mathematics you can do, no physics. Once I know that I have to integrate, the physics is done, and after do the integration and then this plotting business, you get this type of pattern. So the first one is very intense, central maximum is very intense, and after that it is very weak. Correspondingly it is very weak. Actually it is 5%, the first one is 5% of the central one. But once again my eyes are not that sensitive for even higher range or lower range of intensity. So I cannot see whether it is 20 times or what, but here it is. Now width is here, say this first one here to here, this minimum to this minimum, it is 2 times lambda by b, but next this minimum to that minimum, it is only lambda by b. Now recall our single slit. Recall our single slit pattern. The central one was wide and the other one were short. This is it. This is it. The central one, minimum to minimum is 2 lambda by b, but after that every minimum to next minimum is only lambda by 2, lambda by b. So the central one was wide and the other one were short. Okay. Whereas if it is double slit, you have everything cos square delta by 2. So at same distances you will have your minima. So everything is same.
So at origin and its maximum, but the value of theta will be 0 probably at that point. No?
Yeah, that's true.
So how will the intensity be maximum at that point?
Right. So try to do some calculus. Your I is I naught sine square beta by beta square, and you are at the central point. So theta is equal to 0. Now try to calculate this sine square beta by beta square. It's infinity. Denominator is 0. It is 0 by 0, right? It is 0 by 0. So don't think that since theta is 0, therefore beta is 0, therefore sine beta is 0, and therefore the intensity is 0. It will work everywhere else, but not at theta equal to 0, because at theta equal to 0 you have denominator also 0, it will become 0 by 0, and then you have to take a limit. You have to take a limit. When you take the limit, what is the limit of sine theta by theta as theta goes to 0? Sine theta by theta as theta goes to 0? 1. So this 0 by 0 will become 1 or something like that. So this will give you the maximum. But next time when sine beta is 0, when beta is pi, it will be 0. The denominator is not going to be 0. So at all those 2 lambda by b, lambda by b, 3 lambda by b, there it will be all numerator 0, but denominator not 0. Okay. I think we can finish here. Huh? Okay, thank you.